Hello and welcome to Jason Live. My name is Patrick Shea. We're back once again with our STEM career series where we learn about careers in science, technology, engineering, and math from professionals currently working in those fields. Today's role model is Dr. Katie Inderbitzen. There she is. We're super excited to have Katie with us today because she is a former Jason student Argonaut. Almost 20 years ago, Jason helped fuel her interest in science. Now she's made it her career. We'll learn all about the path Katie followed to go from Argonaut to scientist in just a moment. But first, I want to remind all of you out there that this event is both live and interactive. You can use the box just below this video window to send us questions and participate in our polls. We'll try to get as many of you involved in the program today as possible. But right now, it's time to get Katie involved. Welcome, Katie. Thanks for joining us. Great to have you back in Jason.
Oh, thanks for having me, Pat. I'm really excited.
All right. Well, we've gotten a ton of questions submitted even before the event started, so we want to jump in right away and have you tell us about your current career. What is it that you're doing now with your life?
Well, I just finished my PhD in 2012, and so what I'm doing now is I'm researching the underside part of hydrothermal systems, if you want to think of it that way. We're interested in how water flows through the crust, and this is part of the system that we can't see from the surface because it's covered by a whole bunch of sediment and rock. But we know that there's fluid moving around under there, and it's both taken in some places and expelled in other places. And we're really trying to learn over what distances the fluid travels, what's the chemistry like, and even what microbes live down there. So it's a very interdisciplinary process.
So talk to me about interdisciplinary, because on your career profile, you identified yourself as both a marine geologist and a geochemist. And we actually had a question that I will post here from Kendall, and he was curious about that as well. He wants to know, why is it a geochemist? Doesn't geo mean Earth? What's the connection there between the two?
The connection between the two is really because chemists can study chemicals in a lot of different forms. They could study them in the atmosphere. They could study them in an abstract way. But as a geochemist, what I'm interested in is what is the chemistry of fluids and rocks and things like that that deal with specifically with the Earth. Okay, so you could be a generic chemist, but you could also kind of refine your skills and be a geochemist and focus on one very small area of chemistry and how it relates to Earth.
Okay, we've got another question. This one's actually a video question from Noah on this same topic, so maybe we can go a little bit deeper.
Hi, I'm Noah from Turner, Maine, and my question to you is, how do you use chemistry in your job as a geochemist?
Well, that's a really, really great question. So you can see behind me, I'm sitting in actually our chemistry lab right now. But what we do as geochemists, and specifically as a hydrothermal geochemist, is we take samples of the water and we analyze it for its chemical content. And that could be anything from major elements like magnesium and calcium and things like that, all the way down to very, very trace metals and trace chemicals that might be present in very, very small amounts that might tell us something about how the fluid has traveled through the crust, or what microbes might be living there, things like that.
We've got a question came in from Mrs. Templin's class. Let me see if I can dig that up. And they're curious about how you come up with questions for your research. And maybe you can tell us a little bit about the project that you're working on now.
So that's actually a really great question. And actually, I think that's the most fun part of science, is coming up with the questions. And the hydrothermal systems that we're studying, we've only known about for not even quite 40 years yet. And so we're still really just scratching the surface. So right now, we actually have more questions than answers, which is a great thing for all the people who are working in the field. But usually when we try to answer a question in science, we end up coming up with five more questions just based on that one question. So that's the really great part about what we do, is that you're always asking questions. And once you have a kind of subject area that you want to study, it's really easy to generate more questions just based on the research that you're doing.
Okay, and speaking of the research that you're doing, can you tell me a little bit about the Cork project?
Sure. So one of the ways that we use, or one of the ways that we try to study the subsea floor, is we actually use these long-term subsea floor observatories called corks. And basically what a cork is we go out with a drilling vessel and we drill a really deep hole into the crust. And then we put this instrument into it that we cement in, and it seals basically anything that's in the seawater column from any fluids that are circulating around inside the crust. And the reason we want to do that is because if we were to leave the hole open, it would either suck water into the hole or blow water out of the hole, and that's really perturbing the system in a way that we don't want. We want to know what the background state of the system is. So when we put one of these observatories in, you can see on the screen, this is the drill string. We go out with a drilling vessel like the JOIDES Resolution, which is run by the Integrated Ocean Drilling Program. And that's a scientific drilling program, so we never look for oil or anything like that. And we put in a series of casing strings and other engineering bits that allow us to put the instruments in. And then the surface expression of one of these corks we call the wellhead. And at the wellhead, we actually have all of our instrumentation. And we can measure things like pressure. We can measure fluid chemistry over very long periods of time. We can also actually do downhole sampling of pristine crust fluids that are in the crust. And we can sample those for biology and for chemistry. So this is a really great long-term project. We've actually been putting corks in the seafloor for about almost 20 years now.
Wow.
But the program we're working on now is only about 10.
So, related question, Adria wants to know, where do you usually go to collect this data? And a follow-up from Austin, how big are those deep sea observatories?
Well, those are both really good questions. So these data that I've been working on are actually from the Juan de Fuca Ridge, which is about a 20-hour sail off the coast of Oregon and Washington. And so we don't work right at the ridge crest where all the hot water is. We work a little bit further away where there's some sediment cover, because we need the sediment cover in order to drill, unfortunately. And the sediment actually is a very good sealing agent between the seawater and any fluids that are in the crust. So we can really get a good idea of what's going on underneath the sediment.
Great. We've got another question that's come in. This is a combination of questions from Josh, Joel, and Danny. They want to know, how deep do you usually go? How do you get that far underwater? And how do you get that deep in the ocean without getting crushed? Which is always an important part of the project, not getting crushed.
Very, very important. Yeah, you don't want to get crushed. So the depth of most of our observatories on the Juan de Fuca Ridge is about 2,600 meters. And that's about, a mile and a half, give or take. I think it comes out to about 8,700 feet. So that's pretty deep. And at the bottom of the ocean, that far down, the pressure is really high. You're exactly right. How do you do that without getting crushed? So we have a few different things that we can use. One vehicle we've used before is the remotely operated vehicle Jason. And Jason is capable of going way deeper than we need it to go. It can go all the way down to, I think, 5,500 or 6,000 meters. But Jason is controlled from the ship. If you're familiar with the ROVs like Hercules or Argus or things like that, it's a very similar system. There's two arms that we can, pick things up, manipulate things on the seafloor. There's a basket that we can bring our instruments down and back up with. And so that's one way we could do things. We could do it remotely with a robot, or we could actually go down there ourselves. And I've been really, really lucky. I've gotten to do that 4 times. We do that using the submersible Alvin. And so Alvin right now is currently undergoing a refit process. It's going to be able to dive deeper and stay down longer. But we get inside a personnel sphere. It's made out of titanium. And so that's what keeps us safe. And this is a really good cutaway view. There's 3 people. And if you want to think of a good analogy, it's like being in a smart car with 2 people you maybe don't know very well. And you're going to spend 9 hours on a road trip with them, and you can't get out or open the window.
And we're seeing you here. Are these 2 people that you didn't know very well in the smart car?
This is exactly right. This is my first dive in the Alvin. That's me at the left. In the middle is one of my colleagues, Bob Meldrum. And at the right, that's our pilot, Mark Spear. And so you can see it's pretty cozy in there. There's a lot of equipment. And, there's oxygen tanks that, release oxygen for us to breathe. And the little window you can see right down at the lower left-hand side of that photo, that's one of the portholes that we get to look out of. And so we have these little windows, and we also have a video camera system that we can use to look outside while we're in the sub.